We just learned about how a concept called the electric field, or the gravitational field, can give us an idea about the strength of forces in various locations, either near an electric charge like the Van de Graaff, or a mass like the Earth. There's a related concept known as potential, or voltage, and you've learned about this in another video already. But it's kind of the same idea, that we're interested in the parts of a physics concept that depend on location rather than the specifics of a charge or a mass in that location. So potential isn't the location-specific parts of force, it's the location-specific parts of energy. And I want to show you what I mean. I've drawn the same masses I had before, and I want to envision that we're grabbing one of these masses, we'll say this purple one, and we're pulling it out to a higher distance from Earth. In other words, we're giving it more potential energy. And I've done the same with the other three masses as well. So if we were going to look at how much potential energy any of these masses had in one of the two locations, we would take the equation for gravitational potential energy. Now this may not be something you learned in your specific class. Some classes will learn this, some will not. But just like with force, a lot of the equations depend on where you are, and only part of it is specific to the mass you've got. And the reason, of course, is that we started out with all of these objects at the same distance from the center of the Earth. So part of their potential energy was all the same. And the exact potential energy only varied based on their mass. The same is true when we got them farther away. They're all still the same distance from the Earth, but they've moved to an area of higher energy. And how much higher energy? Well, part of that calculation is the same for all of them. So that's something you learned about in the simpler context in the previous video, or 2 videos ago. But we call gravitational potential just the potential energy divided by the mass. It's the part of energy that depends on your location. And if we wanted to figure out how much energy actually transferred for each of these masses, all we would have to do is find out stuff about this location, stuff about that location, figure out the potentials, and then we would just multiply by the specific mass and we'd understand the potential energy. With electric potential, it's kind of the same thing. We have a calculation for potential energy, which I'm not going to go into. And it's going to have things that depend on location, but also have things that depend on the individual charge. So everything a certain distance from the Van de Graaff dome is going to have the same electric potential. Everything a farther distance is going to have the same electric potential. And they will have two different electric potentials between them. And regardless of how much charge there is in any location, that part of the energy calculation will be the same. So electric potential is just the potential energy divided by the specific charge's information. This is much more important to know than gravitational potential. Because when you're talking about gravitational potential, energy changes are mostly about approaching or moving away from one object, the Earth. But in the case of electricity, we often can have objects with lots of different potentials in the same place. An interesting thing happens when you bring different potentials together. And I want to show you what I mean. Just like with potential energy, we have to set a 0 point. We call the 0 point for electric charges the ground, the Earth. And this small ball I have here on a wand, it is wired to the ground. Now, the Van de Graaff, when I turn it on, it's going to acquire a large charge, and that's going to charge its dome to a potential above the ground of hundreds of thousands of volts. Let's guess 200,000 volts. And what that means is when this comes close, charges have a large potential difference. For an individual charge, it has a pretty significant change in potential energy as it goes from one to the other. It turns out that different materials can only handle a certain amount of potential difference across them before they actually break and become charged pieces and allow charge to flow. This is called the breakdown voltage. So let's see what happens when I bring this wand close to our Van de Graaff. So you can see when I bring two different voltages close together, anything between them can actually break down and allow charge to flow. That's one reason we care about voltage. One final thing, notice that potential energy depends on two things, charge and voltage. So I said the Van de Graaff is at hundreds of thousands of volts, but I'm willing to let it shock me. I can go you closer if you want. Maybe not. So why, although I just had hundreds of volts of difference between me and the Van de Graaff, was I willing to do that? Although the V was big, only a small amount of charge transferred. So it wasn't a risk to me because with a small Q, it was a small amount of energy. So anyway, as we go around charged objects, we're always going to care about what is the potential, the location-specific information about energy for every location we're at. And we can use that, combined with the amount of charge we know transfers, to figure out about how much energy is transferring. There's one final thing worth mentioning. Notice that for both gravitational and electric, the lines where we have the same potential, called the equipotential lines, are always perpendicular to the fields. So as the force spreads out, at each location we have the same potential, but we have lessening and lessening potentials as the field is spreading out.